So today we're going to cover Chapter 9, Section 3, and we're going to talk about similar right triangles. Now, the chapter we just finished, Chapter 8, we're on similar triangles, but today what we're going to talk about specifically are right triangles. So the first thing we're going to do is see a theorem, and this theorem states that if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So what it's talking about is this is my original right triangle, the ABC here that I'm outlining in red. Soon as I draw in the altitude for triangle ABC, it now creates two more right triangles. I've got a little blue one over here to the left. It's a right triangle. And then I have another, and I'll do this, outline this one in purple, a medium-sized purple one over here on the right side. All three of these triangles, the red, the purple, and the blue, are now all three similar right triangles. Now, what you're going to be asked to do on the quiz and in the homework is to write a similarity statement for the three right triangles. Now, if it helps you to pull them apart so you can see the corresponding sides a little bit better, then I recommend you do that. Now, when you're doing the homework tonight, you may have to use your knowledge from Chapter 8 and just use similar triangles to match the sides to find the missing side, and you'll be creating proportions. So let me go ahead and pull these apart so we can create a similarity statement. So I'm going to do the original red one first. Now I'm going to go ahead and sit them so that they're all sitting the same way. So I'm going to actually flip the red one over, and I'm going to put the right angle down here. So my right angle was sitting at A, my shorter leg is the C, and then the B was down here. Now I'm going to pull out the purple one, the medium-sized one, and again, I'm sitting them all the same way, and even if I draw the little blue one here. And then my right angle. So now, my right angle for the purple is at D, same thing for the blue. Now, my shorter leg, so my shorter leg here in the blue one is going to be the CD, and then A would be here. My shorter leg in the purple is the A up there, and then the B here. Now when you go to write your similarity statement, it's a lot easier because you can see the corresponding sides. You can see that all the hypotenuses are those diagonal sides. You can see the shorter legs are going up, and then the longer legs across the bottom. So if it asks you to write a similarity statement, let's go with the red one first, and it doesn't matter the order. So if I want to say A, B, C, notice I'm going across the longer leg and then up the hypotenuse. Now you could also go across the hypotenuse to the right angle. That order really doesn't matter. Then when I go to the purple one, I need to go in the same order. So I would go from this leg here and then on around, and then my letters here would be triangle DBA. And then the little blue one, once I match those, it would be DAC. And that would be your similarity statement. So if it helps you to pull them apart so you can see the corresponding sides. So for example, let's say I said that this side of my red triangle was 10, and then this leg of the red one was 8. And then over here, I put an X here, and then I put a 4 here. So you could use your similarity statement now to see the matching sides. So notice AB is going to match with the DA. So that you could put 8 over the 4. And then the 10, which is BC, will match with the AC. So then you could go 10 over x. Again, now you're using a calculator, so it really wouldn't matter. You could do 8x equals 4 times 10, divide by 8, and x equals 5. So you're going to be given the picture, like the original one that was drawn, to find the missing sides, pull them apart, and use your knowledge from chapter 8 to find the corresponding proportional sides. So example 1. Again, I am going to identify the similar triangles. So again, I'm going to do the original large one in red. I'm going to go ahead and write it down here first. STR. Then now once I draw in my altitude, and my altitude can come straight here to the UT, it's now creating the medium-sized blue one and the little purple one. So let me go for the blue one. And then I'm also going to do the little purple one. Now obviously my figures aren't drawn to scale. So once I pull these apart, the medium blue one, again, if you see the right angle on both the blue and the purple, this one is going to be the U and the U. And then for the blue one, it's going to have the T up at the top, and then the R. Let me change that to blue. And then the little purple one, the T will be here, and the S is here. So now, when I go to write my similarity statement, now before I went from leg to leg, let's say you'd rather write your similarity statement going across the hypotenuse down to the right angle. So you could start, it doesn't matter where you start, just the other two have to match the same order that you do for the first one. So if I decided to do the original red one and put it in the order as RST, then when I go to do the blue one, I got to do the same order, go across the hypotenuse down to the right angle. So by pulling it apart, it makes it a little bit easier to see the corresponding sides. And then lastly, the purple one, TSU. Because again, you're going up that hypotenuse to the right angle. If you would have preferred to start at the right angle, go up the leg to the hypotenuse, it really doesn't matter. A good place to start is always use that hypotenuse as a nice reference. So this would be writing the similarity statement for the 3 triangles that are pictured all together. When you're doing the first couple problems in the homework tonight, you're going to be using matching the corresponding sides, your chapter 8 knowledge. When you go to write your answers, it's going to say leave your answers exact. So what that means is you can leave them as improper fractions. You don't have to divide them and make it a decimal. So whenever you see exact, they either want simplest radical form or they want an improper fraction, unless it divides to a whole number. Let's try the definition of a geometric mean. Next, we're going to define what a geometric mean is. And a geometric mean is when you're given 2 numbers, you're going to multiply those 2 numbers and then square root their product. On the quiz and in the homework, you're going to leave your answers in simplest radical form. So, for example here, we've got, this is set up as a proportion. However, when I give you 2 numbers, you don't need to set it up as a proportion. You're just going to multiply them and square root it. But this is leading us into the 2 theorems that we're going to learn, and they're going to be setting them up in proportions. So, for example, here, notice the 2 x's are the same. That gives you x squared when you multiply them. And then this diagonal is a times b, which is here. And then to get the answer, you just square root a times b. And again, you're going to leave it in simplest radical form. So let's try some examples of finding a geometric mean. And again, all you're going to do is multiply the numbers and leave it in simplest radical form. So for example, 4 and 20, All you need to do is take 4 times 20. Now, you can do two things here. You can go ahead and multiply it since you're using your calculator. 4 times 20 is 80. Soon as you hit the square root button on your calculator, you're going to get a decimal. So that's a clue that you cannot put in the decimal answer. You have to leave it in radical form. So this is where we have to do a factor tree. Now, this is where, as soon as you see that you got a decimal as an answer, you could go back to the original and you could do the factor tree right from here and do 2 times 2. For the 20, you could either do 2 times 10, 4 times 5. It really doesn't matter. So if you do 4 times 5, got to keep breaking these down till they're prime. So this is 2. Bring down, it's still prime. The 4 is going to break into another 2 and 2. And then the 5 comes down. Then you look for pairs. I have a pair of 2s. A 2 comes out. Another pair of 2s. Another 2 comes out. This 5 doesn't have a pair. He stays underneath. So now you'll go ahead and multiply these two. Final answer, 4 square root 5. Now let's say you didn't like the factors of 4 times 20. Instead, you wanted to do 8 times 10. It doesn't really matter what two factors you start with because you're going to keep breaking it down till it's prime and you get the same simplest radical form answer no matter what you start with. So even if I keep breaking it down, notice I still got the same thing. A pair of 2s, another pair of 2s, so 2 times 2, and then the radical 5 stays underneath. And it simplifies to 4 square root 5. So this is finding a geometric mean. You just take the two numbers and square root that product. Let's try the next one. So again, if you can recognize that these are both perfect squares, what you can do here is either choose, when they're both perfect squares, their product is also going to be a perfect square. So if I multiply these two, I get 225. And then when I hit that square root button, it gives me an integer. 225 is a perfect square because 15 times 15 is 225. So this one went right to the answer. I didn't have to break down. Now, let's say you weren't using a calculator, because traditionally we do not allow calculators on this quiz. But let's say we weren't. So another way you could have done this without multiplying it is leave 9 and 25 separated. You could do factor trees, or if you recognize that 9 is a perfect square, square root it. Square root the 25, it's also a perfect square. And now multiply 3 times 5. Same answer. So again, if you get something like this where you're not allowed to use a calculator, don't multiply it. Just start doing a factor tree to begin with. This is finding a geometric mean. We are now going to use this knowledge in two proportions that are presented on the next two slides as theorems. And it's going to be a lot of words, but I'm going to try to simplify it. So the first one is called the geometric mean altitude theorem. And this one states that in a right triangle, the altitude from the right angle, so it's this segment coming down from the right angle, splits or divides the hypotenuse into two segments. So my segment 1, so this is the original right triangle here. So this is the hypotenuse of the original. And these over here are going to be the legs. So I have a leg over here. It's the side forming the right angle. And then I have another leg over here. I'm going to do this one in gold. And then I have segment 1 here. It's the hypotenuse that was split into two pieces. And then segment 2. So these are all my parts of the triangle that I'm going to be using in my proportions. So the length of the altitude is the geometric mean of the lengths of the two segments of the hypotenuse. So notice over here is altitude and altitude. So once I multiply that diagonally, altitude times altitude, if it's a variable, like for example, if the altitude was x, that would be an x squared. And then segment 1, and it doesn't matter which one is labeled as segment 1 and which one is segment 2, just label one as 1 and one as 2. So this is the first proportion that we're going to be using. And again, you will have numbers given to you. One of these four, either the blue, the red, or the purple, will be an unknown. And you'll be able to solve for that variable. The second theorem, where we're going to write a proportion, is called the geometric mean leg theorem. And again, let me label the pictures, or the picture. So this I'm going to label as C, this whole thing here, this whole bottom piece. C is going to be my hypotenuse. The X over here, this is a leg, and this is the original right triangle. And then I have another leg, which I'm going to label Y. Y is a leg. And then A is my segment 1. And B is going to be my segment 2. And then I'm going to label my altitude here as a Z. So this proportion, and again, in a right triangle, the altitude of the right angle, from the right angle to the hypotenuse, divides the hypotenuse into two segments. And I labeled them in red and blue, segment 1, segment 2. The length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that's adjacent to the leg. Again, a ton of words here. Now, this denominator over here, segment of the hypotenuse adjacent to the leg. I have an acronym, so you don't have to say all these words. So my acronym for this is going to be the letters S for segment, O for of, H for hypotenuse, A for adjacent, and then L for leg. I call this denominator my SOHAL, segment of the hypotenuse adjacent to the leg. So now that I've color-coded it, so my hypotenuse is this black down here, and it would go here. And then when I go to fill in the legs, I actually have to write a proportion first for the gold leg, and then another proportion for the pink leg. So let me go ahead and do that. So I'm going to be setting it up 2 times. So I'm going to do hypotenuse for both. So hypotenuse. So first I'm going to do the gold leg. So it's going to be hypotenuse over leg, leg over its SOHAL. And the SOHAL for the gold leg is the piece of that hypotenuse, or the segment of that hypotenuse that's right next to the leg, adjacent to the leg. So this is going to be segment 1. That's my SOHAL. Then for the pink one, hypotenuse over leg, leg over its SOHAL, and the SOHAL, or the segment of the hypotenuse that's adjacent to the leg, is going to be segment 2. So for this one, since we have 2 legs, we're also going to be setting up 2 separate proportions because each leg has a different SOHAL. So if you notice, this little proportion that was here goes with this one, and then this one right here is what I just wrote here. So it's written with the variables that I added to the picture, and instead I wrote the words and color-coded it to help you. So now we're just going to do an example of using these proportions. So that's why I told you to duplicate example 3, because it has 2 different parts to it. Because what I'm going to do here is I've made a copy. So this should be part B. I'm going to do part A first on this slide, and then on my next slide, I'm going to do part B. Now, I'm going to label my picture again. I'll color code it for you. So my altitude in purple, and I'm going to call my altitude X. Then I have segment 1 here, segment 2, a leg here, and this leg I'm going to call Z, and then the other leg I'm going to do in pink, and I'm going to call that one Y. And for this problem, they gave me the measurement for segment 1. JR is 16, and segment 2 is 9. Hold on, what'd they give me? EJ. I wrote this backwards, sorry. They gave me EJ is 9 and JR is 16. So they gave me the measurements of the two segments. So in order to find the altitude, I'm going to use my geometric mean altitude theorem. So I'm going to use that one first. So remember that one was segment 1 over altitude, altitude over segment 2. So let's fill in our numbers and our letters. So segment 1 is 9. I told you we're going to label the altitude as X. And segment 2 is 16. I now have a proportion that I can solve. I'm going to multiply diagonally, and I get X times X, which is going to give me X squared. And then I'm going to do the other diagonal, which will be 9 times 16. 9 times 16 is going to be 144. Now, technically, we don't need to, we could have left it as 9 times 16 and then factored it. Now you'll square root it, and X equals 12. So the length of my altitude here is 12, which is in my list of answers to fill in, is the HJ. So HJ is 12. That is your altitude. The next thing that they want me to find is the length of the hypotenuse. And remember, the hypotenuse is here. It's the RE. This is the hypotenuse. Now, for this one, I don't need to do a proportion because they gave me segment 1 and segment 2. So to get the length of the hypotenuse, all I have to do is add segment 1 plus segment 2. So my hypotenuse is equal to 9 plus 16, and that gives me 25. So the length of my hypotenuse, which is RE, is 25. The last two pieces of information are going to be the two legs. So in order to find RH and HE, I have to use my geometric mean leg theorem. So remember that one is hypotenuse, and I'm going to set it up. So I'm going to do two proportions for this one. So I'm going to first set it up using the gold leg, and then gold leg over it's so hall. And remember, it's so hall is segment 1. So I'm going to fill it in. So the gold leg, remember, I labeled a Z. I just calculated the hypotenuse. It's 25. So my gold leg is Z. My segment, and then here, my blue segment was 9. So now I do the cross products. So I'm going to multiply Z times Z. This gives me Z squared. And then I'm going to multiply the 25 times the 9. So I'll do that diagonal. And then that is going to give me 25 times 9 gives me 225. And again, You could have left it as 25 times 9, square root the 2, either way. But now we have to square root it, and z, or that leg, is 15. So this is the length of HE. So HE is 15. That would be a 15 up here. Now also remember, these are right triangles. You can also do Pythagorean theorem to find missing sides if you have 2 of them. Now the next one, last leg that I need to find, hypotenuse over the pink leg. So my pink leg here, pink leg up here, and then over its SOHAL, which was segment 2, the red. So let's fill in what we know. We know the hypotenuse. We don't know the leg length, it's y. And we know segment 2 from the beginning, that was 16. And now I'll cross multiply, y times y, and then 25 times 16. So y squared equals 25 times 16, and that's going to give me 400. Square root both sides, and this leg is 20, which was also RH. So RH is 20, and you could put the 20 up here as well. Last example. Again, we're doing the second row here. This should have been a B. All right, so let's label the picture again. So again, I've got a leg here. We're going to call it Y. We've got this leg. I'm going to call it Z. This will be segment 1. This will be segment 2. This will be my hypotenuse. And then I also have the altitude. So let's fill in the numbers. So we're given JR, which is segment 2. They told us it's 4. Then they gave us the length of the altitude. It's 2. So now we need to go about finding the rest of our numbers here. Now for this, they're going to be left in radical form. They're not going to be perfect squares this time. So let's use our first proportion. We're going to use our geometric mean altitude proportion. So remember that one was segment 1 over altitude, and then altitude over segment 2. This is the proportion we're going to use. So I'm going to go ahead and label segment 1 as X this time. So let's fill in what we know. Segment 1 is X. The altitude length, we know this time, it's 2. And segment 2 is 4. This one we're not going to have to square root. We can just do the cross products. So we're going to go ahead and cross multiply 4 times X. And then we'll do this diagonal, 2 times 2. So we end up with 4x equals 4. Divide by 4, and x equals 1. And remember, x was segment 1, which was the length of EJ. So EJ is 1. RE, that's my hypotenuse. So for the hypotenuse, remember what you're going to do is you're going to add segment 1 plus segment 2. So segment 1 plus segment 2. So this will be 1 plus 4. So my hypotenuse length is going to be 5. So RE, my hypotenuse, is 5. Now for RH and HE, that's my geometric mean leg theorem. So again, we're going to do it twice. We're going to do hypotenuse over the gold leg, gold leg over ipsohal. And remember, ipsohal is the segment of the hypotenuse that it's next to. So that's segment 1. So let's fill it in. Hypotenuse is 5. The leg, the gold leg, I labeled it as Z. And then segment 1 is equal to 1. I'm going to cross multiply. Z times Z gives me Z squared. 5 times 1 gives me 5. I need to square root both sides. So that leg is equal to the square root of 5. So Z equals the square root of 5, and Z was HE. So HE is the square root of 5. And now I just have to do the pink leg. So for that one, we're still doing hypotenuse, but this time it's over the pink leg. So leg, leg, and then ipsohal, that segment of the hypotenuse adjacent to the leg, is segment 2. So let's fill it in. Hypotenuse 5, pink leg is Y, red segment is 4. We're going to cross multiply. Y times Y gives me Y squared. And then 5 times 4, this diagonal. And again, you can multiply it. Because it's not going to be a perfect square, you can do a factor tree from here. But if you happen to have multiplied it, it's 20. But now we got to go back and do a factor tree anyways. So 2 and 2, pair of 2's, 2 comes out, 2 square root 5. So after you square root these, Y is equal to 2 times the square root of 5. And that will be RH. And that's the last piece that we had to find. So that is it for section 9.3. Again, when you're doing the homework, if it says exact and it's not square rooting something, you can leave it and enter it as an improper fraction. Remember the beginning part of the homework, you're going to use your chapter 8 skills of similar triangles and match the corresponding sides. There will be some questions where you can use these two proportions that we just learned. You can also do Pythagorean theorem if need be. So again, anything we've learned is now fair game for solving these problems.